this video will be talking about inertial sensors and in particular accelerometers and how they're used. So basically when we want to measure acceleration and think about accelerations around us when we start walking or when we fall or even just the acceleration pulling us to ground, we're measuring acceleration in a plane, X, Y or Z plane. And to do that, we use an accelerometer. And our accelerometer gives us a measurement as in the units of G. You've probably heard of G forces that pilots use when they pull up in their fighter jet or something like that. Then if we want to measure rotation, and we measure rotation around one of those axes of X, Y, or Z, rather than measuring planar motion here, we're measuring rotation and we use a gyroscope. And the measurement unit there is degrees, like what angle are we at around X, Y, or Z. And we typically call those pitch, roll, and yaw, to use terms that we'd use in aviation. Now, there's several different ways that we can implement these gyroscopes and accelerometers, from lasering ones, mechanical ones, or MEMS ones. We'll focus on in the MEMS ones. They're the lowest cost ones, and they're typically widely used in everything from small inertial navigation systems to even mobile phones. They're quite commonly used in that as well. We'll talk about accelerometer applications first. And one of the areas they use is in navigation systems. And navigation systems, sometimes we don't have access to GPS. For example, when we're indoors or we're underground or in a tunnel or when there's heavy foliage, GPS performs very poorly in those sort of environments. And so we can do integration on our accelerometer data to give us velocity and displacement if we integrate again. We can measure things like vibration, for example, vibration in cars, vibration in motors, vibration in buildings or control systems or machines. For example, if we had a little motor and we put an accelerometer on the side of it, if something goes wrong and that motor starts shaking and going a bit wild, our accelerometer can detect that and detect there's an abnormality compared to what we had previously. We can use them we can put them on animals to do animal tracking, to measure things like animal gait, animal movement, how fast they are, all those sort of things. We have them in our vehicles to deploy airbags when we hit something and we decelerate really quickly. The accelerometer detects that and deploys an airbag for our safety. We can use them for measuring wind loads on buildings and bridges and things like that. We can measure collapses of structures from the vibrations induced in those sort of things and movement. We can use them for detecting earthquakes. We can use them in hard drives to detect if the hard drive's been dropped on the floor, for example, or if it's in midair, if it's in flight, and we can use it to protect that hard drive and stop it being damaged when it hits the floor. We can use them, as I said, as motion inputs for mobile phones. Or I grew up with a Wii remote back in the day, and they've got accelerometers in there to measure your hand position and how hard you hit a ball or something like that. All sorts of different applications for accelerometers. So here, rather than measuring that rotation that we use with a gyroscope, here we're measuring acceleration in a particular plane. So we'll divide it up between our X plane, our Y plane, and our Z plane. And typically at rest, our little accelerometer, and here's an example of one, will measure 9.81 meters per second straight upwards, saying basically if we've got a rest position in the Z plane, it's measuring that 9.8 meters per second because that's the effect or acceleration due to gravity that's on any device. Now, if we turn it upside down, it will measure that negative 9.8 meters per second squared. So the opposite, because we've flipped the plane that it's measuring on. If we drop it, it's in free fall, it'll measure 0 meters per second because it's actually that 9.8 meters per second is acting on it and has moved it, and now it's at 0 meters per second squared. And when we talk about a 3-axis accelerometer, for example, that means that it can measure acceleration in X, Y, and Z planes. Now, I've talked about this term MEMS, the microelectric mechanical structures, and these are very, very small, typically less than a millimeter in size. And they consist of three things, basically: a mass, and that mass is attached to a spring so it can move around, and then some fixed plates. And when you have motion, acceleration, what's happening is that mass is moving on those springs. And we can measure the relative capacitance between the mass and those fixed plates that are there. And based on that relative capacitance, we can measure how much acceleration our system actually has. We duplicate this for each plane. So we have one of these orientated on one plane and then another plane and another plane to give us that 3-axis accelerometer motion. Another interesting thing is what happens if we integrate the data from our accelerometer. So acceleration and distance and velocity are all related by integration. So if we integrate, i.e. We group these things over time, we get our velocity. So we integrate all our samples of acceleration over time, we get velocity. And if we integrate velocity over time, it'll give us our distance. And then if we differentiate, so we go in the opposite direction, we can go from our distance to our velocity, and we can go from our velocity to our acceleration. So we can use an accelerometer to compute both distance and velocity. But one thing we should mention is each time we integrate, and to get distance, we need to integrate twice, we introduce more and more error. The other thing is, because these are incremental in nature when we're trying to measure distance this way, that error keeps on increasing with time because the accelerometer itself isn't perfectly accurate and has some error associated with it. And that adds up over time and gives us a larger area of uncertainty, a larger error, which grows over time. Now, I've talked about accelerometers. Gyroscopes are how we measure rotation around an axis. So we could measure that rotation around the x-axis or the y-axis or the z-axis. And basically we can think about gyroscopes, mechanical ones, first off, about something, a disc that's rotating. And if we spin these discs up nice and fast, we're more resistant to changes when we try and change the axis of rotation. Now, if we mount this in a gimbal, we can actually have these things rotating and we can move that gimbal around, and the gyroscope can keep on spinning in a fairly flat path. Now, we can measure how the gimbal's moved from where the gyroscope is and work out what the angle of rotation around our different axes is going to be as a result of that. We can also see with this diagram here, we've got our spin axis, we've got our output axis, and we've got our input axis. And if we try and rotate around that input axis, the gyroscope will rotate around the output axis and actually move. Now, gyroscopes are nothing new. The MEMS gyroscopes are relatively new because it's been more recently that we've been able to do things on this tiny scale. But the original gyroscopes are hundreds of years old, so 1743, and they were basically trying to locate the horizon in dense fog for shipping applications. Here, they're basically using a spinning top, which has been around for thousands of years. And they've got that principle about if we rotate this spinning top or this device, we've got resistance to the way that we're trying to turn it, and we can measure that resistance and rotation around a particular axis. Now, the MEMS ones, we use, similar to our accelerometers, we use some vibrating masses that are moving back and forwards. We're talking about very fine scales of these things, so much less than a millimeter in size. And these accelerometers and gyroscopes in this MEMS sort of area aren't super accurate. So they're accurate enough for our mobile phones and things when we're using them as an input device. They're more than accurate enough for toys like a Wii remote control where we're moving it around and things like that. But we can't fully rely on the data of these sort of things because they do have a small error associated with them. Having said that, they're relatively low cost and tiny and much more cost effective than, for example, a laser ring gyroscope, which is much more accurate, but also super expensive.